Hello. In the last video, we found the individual mass flow rates for the fuel and oxidizer for our liquid rocket engine. We also found the throat diameter and the nozzle exit diameter, and these are some key parameters. And in this video, we'll continue with the previous example of a hydrolox rocket engine, kind of impractical for the collegiate side, but it's a fun example. And we will basically size our injector holes or orifices and come up with some sample injector geometry. We will be using this this injector orifice or this orifice equation, and it's worth noting that this orifice equation is only valid for single phase incompressible liquids. There are other equations for other things. If you had a gas phase propellant, you might want to use this choked flow orifice equation. And then if you had a two-phase propellant, such as nitrous oxide or something, you might want to take a different approach as well, which we may go over later. But for this simple case, since we have liquid hydrogen and liquid oxygen, we're going to make the assumption that they are both single-phase incompressible liquids, which may or may not reflect reality, but it's good enough for a first-order analysis for this simple case. So you can see we've plugged in some pressure values as well. As you know, pressure always flows from high to low. So the upstream pressure of these propellants has to be higher than the chamber pressure of your rocket engine. Whether you get this pressure through turbo pumps or electric pumps or pressure fed system, blowdown system, it's totally sort of agnostic at this stage, but you can see that we have to have a higher upstream pressure and some pressure drop across the injector. And the literature will tell you that a typical safe pressure drop is about 20% of the chamber pressure. So you want an additional, you want your upstream pressure to be at least 20% higher than your chamber pressure. And you can see that we have exceeded that, and so we have a nice margin to play with here. So with that, let's find our densities for both our fuel and oxidizer. So here's liquid hydrogen at 25 Kelvin. The density is 76.47 kilograms per cubic meter. Plug that in. And this is at 25 Kelvin. We actually don't need the temperature for this, but it's nice to keep track of. And then we will take the liquid oxygen at 100 Kelvin, 1,116 kilograms per cubic meter. And that was at 100 Kelvin. And then up next is the discharge coefficient. That's this C value here in the orifice equation. We're going to just go ahead and plug in 0.6. That's a commonly accepted value for a flat-edged orifice. And this basically just tells you what percent of the theoretical maximum flow are you actually getting through your orifice or orifices or orifice plate or whatever. So sort of like Bernoulli tells you you would get some mass flow rate, but in reality you actually get something a little bit lower than that. And for a flat-edged orifice, 0.6 or 60% of theoretical maximum flow is sort of a commonly accepted value. You can obviously get a more accurate value through testing, but for this first order analysis, we will just go with 0.6 for both. And so you can see it's already done the calculation for the total orifice area. So all I did here was I just plugged in the formula. You can sort of ignore these. This has to do with volumetric flow rate, but we're dealing with mass flow rate. So we can see it's mass flow rate equals discharge coefficient times the total area or the orifice area, square root 2 density delta P, change in pressure. So if you just divide out the discharge coefficient and divide out the square root, you can find this total orifice area, which is what we found here. And then you may want to split that orifice area up into into some discrete number of holes. So in this instance, for this example, we're going to choose a fuel-centered pintle injector. So sort of the fuel will come through the pintle post and then out through some number of holes, and we're going to call it, say, 20 holes, and then it will break this total orifice area up divided by 20, find the individual orifice area, and then get the diameter of each individual hole. And you can see it comes out to just over 1 millimeter, which is a nice value, although it's might be pretty hard to machine in real life, but this is just for the example. And then for the liquid oxygen, we're going to do the same, but since, as we said, we're going to choose a pintle injector, so a fuel-centered pintle injector, so the fuel will go down the pintle post and then through the orifice holes, and then the oxygen will actually come through an annulus gap around the pintle, sort of as a sheet. So what we're actually looking for is not some hole diameters. We're actually looking for the annulus diameter or the annulus area for the liquid oxygen. But again, we'll assume it's a flat-edged sort of orifice type of deal, so we'll use 0.6 as a discharge coefficient, and it sort of calculates the total annulus area using the same equation. And remember, when you're doing the mass flow rate, it's the individual mass flow rate. So for the fuel, it's the fuel mass flow rate, and then for the LOX, it's the LOX mass flow rate, because it's separate for each one. And then it asks us for the pintle outer diameter. I sort of worked up a quick little mock-up in Fusion. I think I chose a pintle outer diameter of 28 millimeters, right? So that's 0.28 meters. And this gives us an annulus outer diameter of 28.42 millimeters. So that's what this looks like. So you can sort of see, here's half of our 20 holes. This is the pintle post. So the fuel would come down here, go out through these holes. Obviously, this is not very realistic, but I just mocked it up real quick. And then the liquid oxygen would come through this annulus gap as a sort of sheet. And hopefully we would get some kind of mixing and atomization and combustion. But as you can see, each individual hole has a diameter of 1.066 as we sized over here. And you could even parameterize this in your CAD, so that if you wanted to change the number of orifices to 30, say, you could have your you could just update the parameter in your CAD and have the holes resize automatically. Might save you some time. But yeah, this is the basic gist of it. How to size holes or an annulus for a simple injector geometry.